Hello, can everyone hear me okay? Excellent. Hi, my name is Mohammad. I do research. Two things. I was reading a book earlier about the color blue. Like red is the best color, but you know, like in science, I like to keep an open mind. I finished reading it. I remain unconvinced. I'd like to start first by acknowledging the traditional custodians of the land on which we meet and pay respect to their elders, past, present, and emerging, especially any Indigenous people here with us today. I am going to walk you through, here we go, some vanadium oxide nanoparticles and why that is sitting here in the frontier, even though vanadium oxide research is well established. For any material science scientists here who think it's established, it is established, but there is something different we are doing. Cool? I'm going to start at the very beginning for what and why we think vanadium oxide is cool. Just a quick intro. Vanadium oxide is a semiconductor. It oscillates between being an insulator and a metal. In the insulator state, it doesn't conduct electricity very well, and it permits infrared radiation. And then when we apply a pressure in the sense of heat, electricity, both, or even sometimes physical strain, we can move it into metallic state where it conducts electricity quite well, and it blocks infrared radiation. This analogy is how I think of vanadium oxide. It's similar to the moon. It has many phases, and what we see is what's reflected. So every stage of the month is a different stage. The moon remains the same. So in a similar sense, vanadium oxide is still vanadium oxide, but then as you apply the stress or the triggers, it starts to shift and move, and that reflectance changes, both, again, from an electronic point of view and from an optical point of view. We only say insulated metal because it is a big change, say, between a crescent and a full moon. But then throughout that change, there's so many things that are changing at the same time. But again, it's more than an on-off switch. It's a dimmer light. It's a gradual change that can be observed very quickly. And the change itself happens in the order of femtoseconds, which is pretty cool. It's a very, very fast change, and fast change is always analogous with fast communication. So that's just like the 101 of what it is and why it's relevant here. All right. What I did in my work, what we did in our work is we created a system with which we can make vanadium oxide nanoparticles that work around room temperature, because undisturbed vanadium oxide only start to switch around 68 degrees, but through our work, we're able to push it down all the way to 36 degrees. It's a big deal because we don't use any dopants, we don't add any extra shenanigans to the compound, because normally people add tungsten, other metals to kind of like shift and change to move it closer. So basically, the status quo with changing that transition temperature is adding more metal, is to physically make it more metallic. So they add tungsten, they add molybdenum and other compounds to shift that transition. But in our work, we purely work with two systems. So we are looking, I'm not going to try and find a pointer. We are looking at physical, intrinsic, and extrinsic strain. Intrinsic strain comes from stoichiometry, in which we control the stoichiometry, or how the compound is put together, and extrinsic strain in the form of silica shells. So we put the compound inside a glass sphere, and that glass sphere adds an extra pressure on the compound to drive it to change at that low temperature. All right. So the outcome is this. The outcome is all these variants of vanadium oxide, and all of this is done on a benchtop wet chemical process. So there's no real limitation of how much I can make of it, like theoretically. I'm sure once you start scale up anything, difficulties will emerge. But at this, as we stand today, there's very, very little, like in terms of hurdle, how, like the amount in which we can make. And that is significant for a lot of reasons, because when we rely like on strain, we have like more engineered control. For example, stoichiometry is controlled here by alternating between cooking it in, like, say, ambient conditions all the way to vacuum, and all those variations, like it's just like a button and a pump. You just change like the pressure of the chamber, and that kind of changes the entire bucket of nanoparticles. And the other thing is the thickness of the silica shell itself as well is another control. So like we kind of like open the toolbox to have more ways to accomplish that low transition temperature without changing the compound itself too much. Because again, that's one of the drawbacks of doping, is that, especially with vanadium oxide, when you are talking about doped vanadium oxide, you impact its optical performance heavily, and you impact its electrical performance, because when you add metals, you're going to change like all the transmission like data. You're going to change all the reflectance, because you're not dealing with just like vanadium oxide. You're dealing with the tungsten, you're dealing with the molybdenum. And then in a lot of publications, if you read about performance, even though the transition temperature is low, the dramatic change is not very dramatic, because again, you're going from like somewhat metallic to metallic, rather than going from like insulator to metallic in this case. And the other application that's important is our work with flexible photodetectors, because generally speaking, if you use evaporation, PVD or CVD, you're going to have to cook vanadium for, I want to say, between 500 to 600 degrees, and that really limits any kind of flexible substrate you put in there if you're trying to layer or you're making a detector. But then if you're only going to spin it or drop cast it, this is all done at room temperature. Like all the photodetector devices we make are all made like at room temperature. You just suspend nanoparticles in solution, you put them in the electrodes, and yeah, you have your photodetector at room temperature, which goes into important things like printing, electronics, and a lot of the things that are really limited by how difficult it is to make the oxide. All right. Yep. It is important to have something that is scalable and repeatable, because I've made vanadium oxide in all the ways that you can make it, and I settled on this one because of the versatility of how you can make it and how much you can make of it and how you can apply it. Again, if you're talking about electronics engineer there, if you're talking about a heterostructure, every material in that heterostructure has its own synthesis dream of how you make it. So if you have two materials that are incompatible entirely in how you make them, you can't make that device, even though scientifically they would gel so well together. In practice, the moment you put like the device, when you put the second layer on top, your device is cooked, because you've compromised the initial layer. And if we're talking from like an environmental point of view, scaling up is very important, because I'll bring you back to the infrared mitigation I was talking about earlier, where limiting how much heat propagates through a surface is one of the important tools in our toolkit if we're trying to combat or limit energy loss, because we have about 60% of our energy usage is to make us comfortable, is to make our kind of day-to-day life, whether it's our homes, offices, or these big tall buildings, comfortable to live in. So if we can create comfortable conditions without expending energy, using like smart materials that can be not only applied pre-construction, they can be applied during construction, and they can be retrofitted. Because we're talking about nanoparticles in a solution. This can be sprayed, painted. This can be, you can do with it in like whatever you would like to do, as long as you are like you're doing it properly. As in, like, I'm not like a spray specialist, but a spray specialist would take this, put it in a canister and spray it on the surface. Again, I'm certain there's more to it than that, but that hurdle is a much smaller hurdle than we can't put that much vanadium oxide in a canister. So now we can put a bunch of it and then do with it what we see fit. Yeah, and all these things are important answers to the question is like, is this fit for purpose? Because a lot of the materials, they are super cool. Like from a scientific point of view, they are revolutionary. But then once you start to have the conversation of, yes, but can we use it? The entire paradigm falls apart. So I embark on my work to make sure that it doesn't. Is this my timer? Yes. Okay. Yeah, this is just literally what I just said. So if you reduce energy consumption, you are going to be saving a lot of money and a lot of resources. And then that would really impact everything if we are discussing mass production, because we're not just individuals, we are consumers as well. And this kind of like reduces the burden on our grid and reduces how, and changes how we use energy, because we need to be smarter about how we spend energy rather than just get more energy, because, you know, it is finite. It's a finite resource. This is just like a cool thing where we reduce the perceived temperature by about 54 degrees. Yeah, I'm pretty happy with it. I'm done.
Thank you, Taha.
I think this is it. Yeah. Thank you, everyone. Staff love.
10 minutes for questions. You might get off scot-free now, Andrew.
If you use it in an actual application, like a window or something like that, show that it actually does with it?
What we did is we used like a simulated hot plate. So we didn't use it on an actual window because like that's a much bigger scale than the laboratory.
Well, a small window. Just a small window.
No, like I'll tell you what we did. In the web. So we have undoped silicon. We coat it, and then we put a hot plate sitting around 180 degrees or whatever behind it, and then we look at the temperature from this side. And that's how we measured that at 180 degrees behind it. We only see like about like 80 degrees from this side, even though we know that it's 180 degrees. So like that's the kind of prototyping we have done. In terms of windows, that would require like climate testing, because like you can put it on a window, it's not a huge issue, but then you need to do like seasonal testing. So you need to put it in a season machine. We test it through the season, see how it fares. But again, like that's this is the like first step of the work. The second step, like this, the smart window study, that's a different study, because that we need to make it first, and we made it. Yeah, using in that specific application is possible, but it's not part of the study yet. Yeah.
Is it meant to reflect infrared or transmit?
It changes the reflections of infrared, yes. Yeah. And it absorbs like a little bit of it just to kind of like keep going, but it's like fraction. So like when radiation comes through, three things happen. Some of it is transmitted, reflected, and absorbed. A little bit is absorbed, much of it is reflected, and very little is transmitted through after the process.
And the intention would be to control that transmission by putting, some power across it, or battery or whatever, to change the properties of it.
No, you don't need to. That's the beauty of it. It's entirely passive. So it just responds to the environment. So if it's hot, it's going to block infrared. If it's cold, it's not going to block infrared.
Okay.
Yeah.
So is that how it differs from lithography glass?
it's dynamic. A low emissivity glass has consistent emissivity. This changes with the environment.
Right.
So yeah, this is on the go tuning for the conditions it's in. But the problem with low emissivity glass is just like once you put it on, it's done. Like it's not adaptive to any temperature, and it's not adaptive to different like climates. Because yeah.
Also by the LCD glass panels, which you apply voltage, you can change the reflective or the
Yeah. You can do that with the same. The chromism is like a photochromic windows where like they physically just limit how much visible light gets in. So those windows are like I think they use tungsten trioxide or molybdenum trioxide mostly, and so what they do is they just limit how much light gets in the visible range.
So is this a cheaper alternative?
It is a cheaper alternative because also this blocks all UV radiation automatically because the material just like takes in all the UV radiation.
Yeah, it's been excellent.
Ah.
Thanks to Taha.
Thank you.